from here actually, and he will speak about evolution and some integral differential model to study evolution. So please.
Thank you very much, and thank you to the organizer to discuss with everyone here. So today I would like to present some work I've done on an integro-differential model that is used by theoretical biologists to study evolution. So first I will introduce a few materials. Sorry. Sorry. Okay, so first I will introduce a few biological concepts that are necessary, and then I will try to study this integro-differential model. So, the first thing that I need to introduce is the notion of phenotypical trait. A phenotypical trait is something which is linked to the genome of an individual. Indeed, it's a physical characteristic of an individual. So the most famous example of a phenotypical trait is the size of the beak of those finches. Historically, that's how Darwin had the idea of evolution. He discovered that in the Galapagos Island there were 13 different species of finches, and the only difference between them was the size of the beak. And he understood that they were all coming from one original species of finches. Okay, so it took a while for one finches to evolve to 13 finches, but for bacteria it's really much faster. So that's why it's really interesting to look at evolution. Okay, so for us, a population will be a measure on a trait, a phenotypical trait, which will be one-dimensional, all right? And we will try to understand the time evolution of this population. The second notion that I need to introduce is the notion of fitness. The fitness is the growth rate of the population. How many, well, if you consider a trait X, how the population at this trait will evolve. So this growth rate, we assume that it has two terms. First term A of X, which depends only of the trait X. Are you or are you not adapted to the environment? And a second trait, which is a non-local trait. And this non-local trait takes into account the competition. You will compete with other individuals that are present in the environment, and well, this will decrease your growth rate, all right? Because the food available will decrease, etc. And here, the thing that is important is that this competition is non-uniform. Usually, that's a very usual assumption for biologists, because the idea is that if you look like another individual, you will compete more than if you are very different from him, all right? That's one of the explanations of speciation. All right, so here are two typical shapes. This would be a maximum at some point, and it decreases and becomes negative if your fitness is too large or too small. And here's the B, it is maximum at 0 and decreases elsewhere. Okay. So this is the model I will study. This model has been proposed by Kimura in the 60s, I think. And it's a very simple one. It just says that the evolution of the population is equal to the fitness times the population. All right? So that's something very natural. And you can add to this the mutations. So in this talk, I will either neglect mutation, which appears not to be so bad if you consider an initial population which is strictly positive, or I will consider diffusion. I will model mutations through diffusion or through a non-local term. All right. Okay. So this model is very easy to implement on a laptop. That's what we have done. And here are some examples. We consider A and a B which have shape similar to the one I presented before. And I did simulation for 3 cases. The only difference being the A here, which is 0.5, 1.5, or 2.5. And what we observe is that in the first case, the population converges to 1 Dirac, so it's not so easy to see it here, but you can trust me. Here the population first seems to converge to 0, but then it branches to two different populations, which each of those populations converges when time goes to infinity to 1 Dirac. A Dirac being for us a species, okay? And here the same with 3 Diracs. Okay, so it's quite a nice model because it allows one to see the evolution of population, but also branching and long time evolution. All right. Okay. So yesterday, Sepide Mirami already talked about a model like this. She talked about a special case where the non-local term, the one I presented was b of x comma y. In what she presented, it was b1 of x, b2 of y. Okay. For the analysis, it's much simpler. It corresponds to the case where you have one resource, one type of food available, and then one can make the change of variable f epsilon equals exponential of 1 over epsilon times u epsilon, and then study the evolution of u epsilon through an Hamilton-Jacobi equation, which is written here. All right. Then the non-local term here would be represented by E1, okay, because this is just a number, and this E1 can indeed be seen not only as a limit of this thing with f epsilon, but also as a parameter which is determined by this constraint, maximum of u equals 0. All right. So that's a very nice thing, and they're working with them, many people that I've written here. But the problem is that if you have more than one type of food, this max of u equals 0 is not enough to determine all those things. All right. So for us, this won't work. And the other problem is that if you study this case with only one food, you know that the population will evolve only to 1 Dirac mass. Okay, that's very general. That's something that biologists know very well. So it's a bit problematic because we won't see any speciation or branching. Okay. So I will try to study a more general case, but today I won't talk about the more general case b of x minus y, but I will impose some assumption of this kernel, which are not biological, but the case I will present includes some cases that biologists use. And then in the last part, I will present the effect of mutations. And for this, I will go to a very simple case, that is a case where we know that the population converges to 1 Dirac mass, let's say at point 0, and I will wonder what will happen if we add mutations. All right? Okay. So this is the assumption I will make on B. It is a operator positivity assumption. Here J can be negative, all right? There's no plus here. So it doesn't only mean that B is positive. It means that, well, it's an assumption. All right, and an example of such a B is a Gaussian, right? Any Gaussian will satisfy this. And this is important because, well, biologists don't really know what this B looks like, and they often choose a Gaussian, all right? And this causes some problems we will see later. Another example which doesn't really satisfy this, it satisfies this with a greater or equal, but this is enough for what we'll do afterward, is a case where you have several food available, that is b of x and y equals this, all right? Now what I will focus on here is the long time behavior. I won't be able to describe, as Sepide did yesterday, the evolution of the population. I can only describe what will happen when time goes to infinity. So what I expect is that the population converge to an equilibrium, and that this equilibrium will satisfy a stability condition, which I have written here. This stability condition, well, it has two things. First, the fitness of f of the population should be equal to 0 at the traits where there is a population. This is just saying that it is a steady state of the equation I had. And the second condition, which is that the fitness should be negative elsewhere. All right? Otherwise, you could imagine that you introduce a mutant at this point and it will increase. All right? An example of such a population is this one. You consider A and B two Gaussian, and then you can check that f bar chosen like this one is indeed an ESD, because if the fitness is A minus B convolved with f bar, and if you convolve those two Gaussian, you obtain exactly this one. Right? So this condition will be satisfied everywhere. And indeed, the biologists know this very well. They have computed this, and it is kind of a problem because f bar here is not a sum of Dirac masses. In the simulation I showed before, you saw that the population converged to 1, 2, or 3 Dirac masses that we could interpret as different species. But here we have a continuum, so it's not really clear what it means biologically. Okay. The first thing that we get from the assumptions, the positivity assumptions that we made, is that there exists only one ESD. Okay? How to prove this? We just write here the condition of an ESD. We had that the fitness should be negative. All right? We can multiply by the population. So F1 and F2 are two ESD. We multiply by F2. This is still negative. And since A equals B convolved with F2 bar on the support of F2 bar, we can replace this A by a B convoluted with F2 bar. Okay? Now you can just exchange the 1 and 2 indexes because it is a symmetric problem. And if you add the two inequalities that you have, you get this inequality here. And you recognize here the positivity assumption that we made, that is b of x minus y times something depending on x times the same thing depending on y. So we know that this is positive if f2 is different from f1. Okay? So we have shown that there exists at most one ESD. The second thing that this assumption brings is that there is an entropy. The entropy is this one. So it looks very similar to the entropy of a Boltzmann equation or whatever. It would be the relative entropy of f bar with respect to ft. So it's a bit strange because usually the contrary would be f of t log of f of t over f bar. Okay, but apart from this, it has the same shape. In particular, it is positive. And if you differentiate this one, you will get two negative terms. One, this one, which is just the fitness of f bar, that we know is negative everywhere, times f, which is positive. And here, minus something that we know is positive, thanks to the positivity assumption. Okay, so it decreases. It decreases and it's bounded from below, so you get that the derivative goes to 0, and the derivative indeed contains these terms, which turns out to be a norm on the space of measure. All right. It's not a norm that the topology of this norm is not the one that we usually use for measure, but it defines a topology, a very weak topology. And that's all what we can get. So this is not really true. Now there's a problem because I told you that usually the asymptotic population is a sum of Dirac masses. Okay, and here in the entropy we have f bar log of f bar and this has no meaning if f bar is sum of Dirac masses. Okay, so this indeed will only apply to situation like the situation of Gaussian that I presented before, where f bar is an L1 function, L log L function. All right. So that's not so satisfactory, but indeed there's a trick. We can notice that this can be decomposed as f bar log of f bar plus f bar log of 1 over f. So if we just remove the f bar here and replace it by a 1, we just subtract, let's say, a constant, which is infinite, but it's a constant. So that's what we do. And we still have that this modified entropy is an entropy, all right? It will be decreasing because the time derivative of this one will be exactly the same as the one before. The only thing that we lose in this process is that now this entropy is not always positive. Indeed, it will converge to minus infinity. That's a bit of a problem, but we're quite lucky because indeed we can show that this entropy cannot decrease too fast. Okay, it cannot decrease faster than logarithm of t. And if we bound something which is decreasing by a logarithm, it's indeed enough to show that the time derivative goes to 0. Well, we have some other arguments, but that's the idea. Okay. Now, as I said, we can apply this to the Gaussian case that we had before. That is, if we consider A and B, this continuous function is indeed globally stable for the system. So that's what we can see numerically, but that was a question that some theoretical biologists asked because it's surprising to see an L1 population that is stable. But then biologists, no, but before we did anything, right? But they noticed that indeed those population here, this Gaussian steady population is not structurally stable. That is, if you change a bit the A or the B like this, instead of 2 you have 2.05, you won't converge to the Gaussian anymore, but to a sum of Dirac mass here. All right. So that if the Gaussian is stable but structurally unstable, it doesn't make sense, right? Because you will never get something like a real Gaussian in natural conditions. But indeed, from our previous result, we can make a corollary, and this corollary says that if you modify a bit the coefficients A and B, the ESD won't change too much. All right. So indeed, you have a structural stability, but this stability occurs for the weak norms that we had, the weak norm of measures. And indeed, if you make numerical simulation and let this perturbation goes to 0, you will notice that this population, which is a sum of Dirac masses, evolves and seems to converge to a Gaussian. Okay, so well, from a biological point of view, I'm not sure that helps a lot, but well, indeed, it has a meaning to the weak convergence in sense of biology, because if you have some measure, you will have some noise, and you are not able to distinguish whether it will be a Gaussian or a sum of Dirac masses close to the Gaussian. Okay. Now, what happens if we remove this positivity assumption on the B? Well, everything that we have done so far breaks down. We don't have an entropy anymore. It's not decreasing. And we don't even have the uniqueness of the steady state. Here is an example for some A and some B. You choose two different initial data, and for the first one you converge to 2 Dirac masses, and for the second one to only 1. So in this case, we cannot expect a global stability result like we had. we can only do local stability of those sum of Dirac masses. Okay, that's possible. Theoretical biologists do this all the time. They call it ESS, CSS, or evolutionary attractors. And we can show that those concepts indeed extend to those PDE models. But I don't want to talk about this today. I will talk about the effect of mutations. What happens? We consider a population which evolves to 1 Dirac mass if we neglect mutation. What happens if we add mutations? Okay, that's the idea. So a very simple model where we know that the population will converge to 1 Dirac mass is typically like this. A is concave, strictly concave, and the competition is uniform in the population. So we will consider models of this kind of perturbation of this model, let's say. If we choose diffusion to model mutations, we can compute explicitly for this this A and this B the equilibrium, and the equilibrium will be an exponential, a Gaussian. All right. So if you look closer to a Dirac mass, indeed it will have the shape of a Gaussian. So biologists know that well, and so they think that when they do numerical simulations of those things, they will fit the population with a Gaussian. What we were wondering is what happens if we, instead of modeling the mutations by a diffusion, we use a non-local term, which is closer to what you do when you run simulations, and which might be closer to the biology. I don't really know. So that's what we do. We consider a model like this with a non-local term modeling the mutations. And the idea then is to put an epsilon here and to look at the asymptotic shape of f epsilon. So first what we did is to prove existence of steady states of this equation. This is not so obvious. It was obvious for the case where we had a Laplacian here, because the Laplacian has regularizing effect, so you can apply a Schauder theorem. It's a bit more tricky, but it works. The idea is that, well, from this equation here, you can divide by the fitness and obtain that f bar, a steady solution would write f bar equals mutation convolved with f bar over minus the fitness. And so you choose a functional which writes like this. And for a delta well chosen, you can show that there's a set of function of L1 functions that is invariant by f. And then you are able to apply Schauder theorem and to show that there exists a steady solution indeed. Okay, so now we know that there is a steady solution. What does it look like when the mutation gets smaller and smaller? Well, we have some complicated assumption, but basically it says that it's more or less the case where A is concave and B is constant. All right? And we have this result. We have that f bar indeed looks like 1 over 1 plus x squared. All right? So it doesn't have the shape of a Gaussian anymore. It has a shape of a Cauchy profile. All right? So we haven't discussed with biologists or theoretical biologists about this, but well, close to 0 it would have the same shape as the exponential, but if you look at the tails, it's different, so I don't know. And to show this, we use once again we rescale the equation with epsilon to look closer and closer as the mutation go to 0, because we know that thing concentrates. And then we use just the same trick as before, that is the population is equal to the mutation term over the fitness. All right. and we guess that the shape of the fitness is a constant, well, minus the fitness is a constant plus something times x squared, right? And we are able to determine this something, q epsilon, through an integration. We integrate this one, and it makes 1 equals integral of 1 over q epsilon plus something times x squared. Okay, and this way we are able to show the asymptotic that I showed before. Okay, so that's the end of my talk. So just a few conclusions. For theoretical biologists, those integral equations might be interesting. Some are using them because you don't have any stochasticity. So if you look at very large population of bacteria, for instance, it might be interesting to remove stochasticity if it's not necessary to the comprehension of what happens. Then it's interesting compared to other deterministic model because you can use only one model to model everything: evolution, branching, and long time properties of the population. And finally, numerics are very fast, because what biologists usually do is they do what they call individual-based simulation. That is, they consider a population of n individuals and just let those evolve. But it takes really a long time to obtain something. So here it's much faster. Okay, and they have many interesting questions, mathematical questions, because there's a community which is very theoretical, and well, it's interesting. So thank you very much.